Okay, so welcome everyone to the Oxford Discrete Mathematics and Probability Seminar. As usual, we've muted people. Please feel free to ask questions in the chat, and we'll interrupt if it seems a good point to interrupt. Also, there are co-authors in the audience who might like to answer questions in the chat as well. So this week, it's a great pleasure to have Ashwin Sah from MIT, who's going to talk on friendly bisections of random graphs. Thanks.
Thank you, Alex. Let me share my screen. Does this look okay? Thanks. So as mentioned, I'll be talking about friendly bisections of random graphs. There's a lot that can be said about this area, so I won't be able to say everything, of course, but feel free to interrupt about anything particularly interesting that catches your eye. Just before I begin, I'll mention that this work is joint with Asaf Ferber, Matthew Kwan, Bhargav Narayanan, and Mehtaab Sawhney. All right. So let's just talk about a very related notion in general, which is that of cuts, max cuts, and min cuts, which will be very related to the notions that we'll discuss today, that of friendly partitions. So to begin with, we'll say a cut of a graph is a partition of the vertices into two sets, which are non-empty. And the size of the cut is the number of crossing edges. So as you might recall, a max cut is a cut with maximum possible size given a graph, and a min cut is a cut of minimum possible size. And at least for dense graphs, for example, min cuts are usually much less interesting just because you could have like one vertex on one side and the rest on the other side, and that would most likely be the best thing to do. But it is still a useful notion, and as we'll be talking about bisections later, min bisections are perhaps more interesting in this regime. All right, now given a partition, we'll say that the friendliness of a vertex is basically the degree into its own part minus the degree out of its own part. So sort of how friendly it is within its own part. So if V is an A, I take the degree into A minus B, and similarly reverse. And perhaps the key thing to note here, and that will sort of connect these two notions, is that if I take a maximum cut, then every vertex is, I guess you could say, unfriendly. There's sort of an issue of when this delta AB of V equals 0 exactly, should we call it friendly or unfriendly or both or neither? I won't really care for the purposes of this talk. And it turns out that even like off by one errors in terms of what this quantity is won't really matter to us too much. But for some of these problems, it actually matters more. Although we're going to be talking today about mostly GN1/2, and it turns out that it has some pretty special sort of anti-concentration properties that tell you don't really need to worry about like off by one errors. But here's sort of the basic thing for now, at least, which is that I guess you always have an unfriendly cut just by taking a max cut. Okay, so that's sort of a motivating example as to why you might care about certain partitions which are balanced in terms of their vertex degrees in certain ways. It's related to this max cut notion, which is studied quite a lot. Now, on the contrary, a minimum cut does not need to be friendly. So as I said, a maximum cut is unfriendly. So you'd say, well, maybe a minimum cut should be friendly. But that isn't quite true. And it's kind of for the reason I mentioned earlier, which is that if the max cut has one vertex on one side and everything on the other side, then there's no way that the vertex can have a lot of neighbors. Sorry, I might be getting the sign wrong. But basically what happens is in this argument to show that the max cut, that every vertex is friendly, what you do is you just take a vertex, which is friendly, and you switch it to the other side. So if I have a friendly vertex, if I switch it, that'll increase the cut, which would be a contradiction. And so everything must be unfriendly. And you'd want to run a similar argument here, except that you could potentially make the vertex partition trivial by doing this. So it seems a little more subtle for minimum cuts, but it turns out that Stevens showed in 1996 that regardless, there's still a cut in every such graph where maybe you don't know that everything has delta AB at least 0, but you have that as at least -1 instead. So it's almost fully friendly. So almost what you get out of sort of a max cut argument, but maybe off by 1, which again doesn't really matter too much for us. So from this, you can actually pretty easily show that GN1/2 always has a friendly cut. Now, there are a couple of related questions that have been asked in this area that I just want to mention at the beginning to give an idea of the other sorts of things that people study with regards to these sorts of cuts. One of which is this conjecture of Kwan and Lineal, which is that for any D, there are actually finitely many D regular graphs with no friendly cut. So again, we won't really be concerned about these off by 1 issues because in these dense random graphs, it doesn't matter. But in general, you might ask, well, okay, Stevens showed that you can almost be fully friendly, and can you actually be fully friendly? There shouldn't be that much of a gap here. And Bond and Lineal are conjecturing that if I look at a D regular graph, not only is it sort of almost all graphs work, but actually literally all but finitely many graphs work. And this is perhaps sort of related to a theorem of Lineal and Louis, which is that for even D, a random D regular graph has a fully friendly cut with high probability. So you can think of this as sort of a partial result towards this Bond Lineal conjecture. All right. So hopefully this gives some idea of the types of, I guess, graph by partition questions that are being asked with regards to the balance of the vertex degrees. So again, just to recall, this delta AB is always going to be the degree into your part minus the degree across. All right. So let's talk about bisections, because these are much more subtle for a lot of reasons. So to begin with, let's look at a max bisection in a graph. Similar start to before, max cut, max bisection. With a max cut, we could say, well, if I have a vertex which satisfies some degree discrepancy property, I can always switch it to the other side and get a bigger cut, which would be a contradiction. But with a bisection, let's say that the graph always has an even number of vertices for simplicity. If it's odd, you could just take, an almost bisection. With a bisection, I need to switch one vertex on one side and one vertex on another side simultaneously to maintain the property of being a bisection. So what you can deduce from this is that if I have a max bisection, I cannot have a vertex on both sides, which is both has friendliness strictly greater than 0. That is, I cannot have a vertex on one side who has many more neighbors to its own side and one vertex on the other that has many more neighbors to its own side, because then I could switch both of them simultaneously. And regardless of whether there's an edge between them or not, it turns out not to make a difference, and the bisection will go up. But this sort of leads to an obvious problem. The fact that I need to switch something that is friendly on both sides instead of just one side with max cut. What that means is that I could secretly have one side be all of one type and one side be all of the other type, and never be able to switch a pair of vertices to increase the cut. One side is, unfriendly as you want for a max bisection, but the other side is, barely not. And every time I switch any pair, the bisection doesn't go up. And so I can't exhibit a contradiction. There's sort of this sidedness behavior that happens because the bisection needs to be balanced. And so I need to switch pairs instead of individual vertices. So despite this, Füredi conjectured, I think in the 80s, that in GN1/2, with high probability, there still is a bisection such that every vertex is friendly. And similarly, every vertex is, or with almost all vertices friendly. And similarly, you can ask a similar question about unfriendly. And for the case of bisections, these are almost symmetric questions. And so they're almost the same, again, up to some off by ones. So with just to sort of clarify for everyone, keep in mind that like a max cut or a max bisection will correspond to unfriendliness, because a max cut really wants to have more neighbors across. And a min bisection is going to correspond to friendliness, because a min bisection wants to have fewer neighbors across. Again, in the case of bisections, basically by complementing the graph, it turns out that this doesn't really matter, the difference between friendly and unfriendly. So I'll talk about the original conjecture, which is asking for a friendly partition. So we will be talking about minimum bisections later on. And I'll just mention one related question given by Bosch and Alex Scott, which is that in any graph, there's a bisection where the difference between the degrees, so I think the degree into your own part minus the degree out of your own part, is at most 1 for all b. So this is sort of like an almost version of one of the previous results, but one of the previous sort of obvious results, except for bisections inside. So this is something that you can ask more generally about any graph. And today we're going to be focusing on the case of the random graph and friendly bisections. And I should just note that actually, if you can prove their conjecture, it actually implies Füredi's conjecture with some additional properties of Gn1/2. And again, the fact that complementing doesn't really change anything. If you resolve their question, the positive, of course. All right. As mentioned, unfriendly and friendly are all quite similar. So for today, we're going to really be talking about, I have Gn1/2, or I guess G2n1/2. I want to split into 2 parts of equal size, such that the degree in my own part is always at least the degree across. And so our result is that this exists with high probability. That is confirming Füredi's conjecture. And I should also note that, in fact, we give sort of an algorithmic way to find such a bisection. All right, are there any questions about, what's done so far or anything like that? I'll just wait a second. This is sort of the main thrust of the talk, so to speak.
Just to check, we had one question. So the statements for all v, not just for all but a little on.
Oh, sorry, I made a typo. Yeah, sorry. It should be almost all v. I think I was editing the statement slightly, and then thanks for that. Yes, it should be almost all v in this theorem. So also this question of yours and Bosch is actually a little stronger because you're really asking for all v also. And that distinction is an interesting question to ask about whether you can legitimately do it for all v. But we're in Gn1/2, so we really want an almost sort of statement here. Yeah. Sorry about that. Yes, it should be almost all v. Great. Good question. Okay. I'll continue. So let's start with sort of a simple idea, which builds off of the original idea, which is to take a minimum bisection. So for sort of technical off by 1 reasons, if you consider a minimum bisection, you can show that there is a bisection such that either on one side, everything is basically friendly, or on the other side, everything is basically friendly, where basically is off by 1, which again won't really matter for us. So let's just pretend it means that it's friendly. And again, we have this problem that maybe one side could be fully friendly and we're all happy, but the other side could be fully unfriendly. And the question is, how do you rule out this conspiracy that there are no good swaps to increase or to decrease the minimum bisection further and further? This is sort of unnatural because if you think about it, this really, okay, maybe this configuration exists in a random graph, but this shouldn't really be the minimum bisection shouldn't really look this unbalanced, maybe. Maybe not. So the idea is to sort of try to find a minimal, I guess not necessarily minimum, but we just need a minimal bisection. And we want to find such a minimal bisection in a way that's sort of symmetric by just sort of greedily randomly coming to it somehow. So what we do is we start with a random bisection of G and 1/2. Then we repeatedly choose a pair of random unfriendly vertices. So they have more neighbors across, and I'll just swap them. And every time I do this, the bisection will go down, or there's an off by 1 issue. It doesn't have to go down, but it won't go up. But over time, you'll expect it to go down. And you keep on doing this until eventually you cannot. Now, by this lemma, we end in a bisection where one side is fully friendly, or okay, fully almost friendly, anyways. And the key idea is that the process I just described is a very symmetric process. One side or the other isn't really privileged with respect to each other. So if one side is fully friendly, probably both sides should be fully friendly. You can think of this as saying somehow like there's no sort of phase transition that happens where suddenly out of magic, one side starts to get preferred halfway through the process or something. Maybe that could happen in some sorts of processes, but this is such a simple process. And there are reasons you might expect that that's not going to happen. So one way to formalize this is, let's consider this random process and let x sub t be the number of bad vertices after t swaps. If we can show its variance on one side specifically. What if we can show its variance is little o of n squared? So it's concentrated on the scale of n. Let's say for all times. Then we're actually done. Because then, by symmetry, y sub t, which counts bad vertices in B, is also concentrated around the same value. And so then basically you show with high probability, x sub t and y sub t are going to be near the same value, up to little o of n. But I also know that at least one of x sub t and y sub t is basically n, because I'm in a minimal bisection. I can't go down any further. So both sides are approximately the same because of this concentration and symmetry argument. And one side we already know from minimality has to be the full thing, basically. And that tells you that both sides are equally friendly, equally good. And so almost all of the vertices are good. This is a simple idea, but also sort of a powerful one, because it allows us to get access to this without necessarily knowing too much about the structure of this minimal bisection that we're looking at. The question, of course, is how would you prove this concentration? And so that's sort of what we're going to talk about for the remainder of this talk. Concentration of this swapping process. Okay, so I explained why this should finish. And now it's just a matter of showing. So one sort of natural thing to try is, various concentration inequalities that have appeared along the years. One natural one is Stein, which states that if we have a function of independent random variables, then its variance can be bounded in sort of a specific way, where basically you take the sum over possible kind of like variances when you resample each coordinate. Now, in order to use this, what you do is you can imagine some x sub t is a function of all of the edges of G on 1/2, as well as the initial random bisection that we start with. Because based on those, this gives me a random process, x0, x1, x2, etc. X sub t is just some function of these. And you want to somehow show that each edge is not very influential. And that would be enough. However, there's sort of a weird thing that can happen. If I flip off a single edge somewhere, at some point along the process, that could affect the outcome of a single sort of edge swap. Okay, well, that shouldn't be that big of an influence. But instead of swapping 2 vertices, I swap 2 other vertices. That affects everyone's degrees by 1. Now that everyone's degrees are affected by 1 after 1 step, maybe there's a problem and it affects the next step. And now, the degrees are modified by a bit more. And then more and more and more. And you can have this sort of contagion that happens. And it's really hard to rule out you might expect that this doesn't really affect the process too much, but it's actually really, really hard to rule this out. So this is actually, at least for us, to bust. We don't. I actually am not aware of an argument that uses this approach. So while it's a good idea, some of these high dimensional concentration results seem a little tricky because it's hard to analyze the influence of a single edge in this, very long iterated swapping process that goes on for potentially like n squared steps. Actually, it should only go on for like n to the 3f steps, but even so, that's quite a long process. All right. Another possible approach one can make is using what's sometimes called the differential equations method. So this is something that has seen a lot of use and really a lot of progress when analyzing certain random graph processes like H-free processes, as well as like random triangle removal processes and other such things. And the way it works is I have this random process in a graph. As a simple example, I have Kn, and I randomly remove triangles at every step, a uniformly random triangle. And I want to show that I can sort of, when I do this over time, I cover all but a little one fraction of the graph, something like that. What you can do is find a ensemble of random variables that sort of self-propagate in a certain sense. So in the case of triangles, the triangle removal process, what you do is for every edge in Kn, you study the number of vertices that are connected to both endpoints. And after running one step, you look at the expected change in each random variable. So we have n choose 2 different random variables in this particular case. And you show that this expected change can be approximated in terms of the variables that we already know. Okay. I mean, once you have that, you're sort of in an almost like a martingale situation. Specifically, you can sort of approximate the system by some sort of differential equations, and you solve this differential equation to obtain an ansatz of some form for the trajectory of what this random process is going to look like. Then you basically subtract off that main term, and you're left with something that kind of looks like a martingale, or maybe like a super or sub martingale. And you basically use martingale concentration to show that the process stays near this trajectory over all time. This is a pretty general process. I don't really want to go into the technical details, but it's seen a lot of great use in various areas of random graph processes. And you might wonder whether we can apply such an idea here. A very powerful idea. One thing that sort of is hard to get around in our case is that, for example, in this triangle removal process, at every stage, I have a new sort of completely random triangle to work with. Or in the H-free process, I'm adding in new randomness at every step in terms of the graph structure, independent of the graph structure in some sense. Not exactly, but there's a lot of randomness there. And certainly our swapping process has some randomness because you can choose the vertices randomly. But in order to inject that extra randomness of, swapping a pair of unfriendly vertices to try to make them friendly, there's a cost associated in our case, which is you have to reveal information over time, which is way too much. So in the triangle removal process, for example, you just reveal these sort of co-degrees almost, and you evolve them over time, and you can really control them because at every step I'm injecting randomness that affects the co-degrees of the remaining graph. And so there's something to work with. But in our case, in order to analyze a single swap, I need to know who's unfriendly. And to know who's unfriendly, I need to know basically every vertex's degree to every part. or at least some statistical analog. Then at the next step, I need to reveal the degrees after swapping. And if I have V1 and V2 and I know everyone's degrees, first off, to each part, and then I swap them and I know everyone's degrees again, then I basically know who connects to V1 and who connects to V2. And if I keep on doing this, if I reveal too much information, and you really do need to reveal a lot of information if you think about it, within maybe O of n steps, I know most of the edges in the whole graph in a very strong sense. And remember, we need to run this for n squared steps, or really n to the 3/2 steps, but we have to run this for a lot of steps. And it seems like the amount of information revealed at each step is just too much. You lose too much for the gain. And so it's not clear how to run this differential equations method as has been done for these other processes. All right. Are there any questions about sort of the two approaches mentioned so far? We're going to jump into what we actually do in just a second. Or any of the other background that I've talked about. Okay. So let's get into some of the ideas that are in how we actually prove this. And some of these ideas I think are really interesting. I unfortunately won't be able to go into all of them in great detail, but I think trying to get some of the broad ideas might help a lot. So the first idea is to not swap one vertex at a time, one pair, and do it in sort of a nibble. So at every step, we're going to swap epsilon n, the epsilon n most unfriendly vertices on both sides, or something like that. In reality, we do something slightly more complicated for technical reasons, but you can basically think of it as swapping the epsilon n most unfriendly vertices at every step. Okay, and why can we do this? Well, it's sort of twofold. The first thing to note is that this sort of average or summed friendliness is always around n to the 3/2 in size for every bisection simultaneously with high probability. And this actually just, I won't prove this part B here, but so this sum over these friendlinesses is very closely related, I think, by a linear combination to the max cut, or sorry, to the bisection cut size minus like n squared over 4, n squared over 8, maybe, so something like that. If you do things out appropriately, maybe with some other things mixed in, but basically the point is what's happening here is that you expect a max cut, or you expect any cut like bisection in a graph to have cut value n squared over 8 plus O of n to the 3/2 just by a union bound, and sure enough. So what this amounts to saying is that the total friendliness, you expect it to really be like an n to the 3/2 phenomenon. So in our, I've already sort of touched on this, but in our original approach, when we swapped a pair at a time, and maybe you'd gain by 1 every time, you'd expect to take n to the 3/2 steps. Then that's very naive. Okay, but part A here is saying that you can actually do a bit better, which is that at every step of this random process, I claim that you can actually always not change the sort of cut value by 1, but by root n, if I swap a pair of vertices. And then finally, the third idea on top of that is if I swap epsilon n vertices simultaneously, that should change it by epsilon n times root n. Okay, so we'll get to that. We'll get to that in just a second. But let's start by proving this sort of A. So what A is saying here is that I take a random graph and I take any bisection and any vertex, or I take any bisection and I look at the vertices for which this friendliness value is large. I want to claim it's almost all of the vertices. equivalently, if the friendliness value is small, then I have very few such vertices. And this is in all bisections simultaneously. Okay, so let me just give a quick proof of this. So the first thing to note is that if we fix a partition and we fix a specific vertex and we look at its friendliness value, this is just a sum of a bunch of Bernoullis minus a sum of a bunch of other Bernoullis. And so this is basically just a Gaussian. So if I fix some constant c, we see that the probability that the friendliness value is less than c root n in magnitude is around O of c. All right. So what we can do is now look at the probability that we take a specific set S of epsilon n, at least epsilon n vertices. The probability that this whole set S satisfies this particular property is now the same thing raised to the epsilon n power, which is exponentially small. And so if I choose this constant c appropriately, I can actually make this probability so small that it's less than, 100 to the negative n. And finally, we can just take a union f over a, b, and f. So the point here is that it's very unlikely that a single vertex has like little o of root n friendliness. It's very unlikely that a specific vertex is very close to balanced. Most vertices are like root n away from balanced. And so, okay, you could have one vertex that is little o of root n, but you can't have n vertices that are little o of root n by sort of boosting the probability using this tensor. Okay. So here's the idea. And I think I have a typo here. So suppose I have many unfriendly vertices on both sides. So I think this should say friendly in both cases. So suppose I have many unfriendly vertices on both sides. Then what I'm going to do is I'm going to, as I already said, I'm going to take epsilon n vertices on both sides. And let's take the unfriendliest such vertices. Okay. Part A tells us something very funny. I know already that I'm taking unfriendly vertices. So I know that, delta AB is already like less than 0. And I know that all but a very small number of these vertices have order of magnitude root n. And therefore, the most unfriendly vertices have their unfriendliness lower bounded by root n. They're very, very unfriendly. And then we swap them all at once. So again, as I sort of mentioned earlier, I have around epsilon n vertices on both sides. And each of them has like a root n unfriendliness to them. I swap them all at once, and you'd expect to gain like epsilon n root n. There are some sort of cross terms that are involved, but believe me when I say they don't really matter. Okay, so I do that once, and then I do this a bunch of times. And this fact, part B, tells me that I can't do this forever, because every time I'm increasing the total friendliness. And the total friendliness is always between negative 100 n root n and 100 n root n. So this can only happen some constant number of times. Okay, this is much better than before. Instead of having to analyze n squared or n to the 3/2 or whatever many steps of our original swapping process, now if we use this approach where at every step we take the epsilon n unfriendliness most and swap simultaneously, this analysis basically tells us that we only need to analyze O of 1 steps of this algorithm and show the concentration after this many steps, which is much, much better. You could imagine that you could reveal information at every step to precisely balance that out, or at least be able to still control what's happening. Are there any questions about the broad ideas here?
Not really. It's more a comment that you're presumably hiding lots of details there. That the statement about the set S is not independent for different V, and you have to presumably fiddle around somehow to say that doesn't matter too much, and so on and so on and so on. So I'm guessing it's
Yeah.
not quite as simple.
Well,
as your-
okay, so I mean, I
just-
think what I wrote here is a proof of part A of the lemma. But in order to then apply this lemma, yeah, you have to do various things. Is there an issue?
Doesn't look like no, because for different V and S, these events are not independent. The
Oh yeah,
delta
no,
of
sorry,
them is
sorry.
something different.
Again, what? Okay, let's review. Let's fix some partition and a vertex and a set, and let's look at the probability that in the completely independent model, delta AB, like delta AB of V is at most C root N for all V and S. For like, I am not treating A, B, V, or S as random variables here. I fix specific possible sets, and I look at the probability that this particular set S satisfies this property in the completely independent model. This is a valid bound on that probability. And then at the end, I'll take a union bound over possible A, B, and S.
I don't think it is a valid bound without some further argument, because the edges between the different vertices in S.
There's a slight issue if the vertices are on opposite sides of the bipartition, but you can just look at one side of the bipartition.
Yeah.
And then there are epsilon n over 2 of them.
Yeah.
And those you can just treat as genuinely independent. You just reveal half the graph. You just reveal everything else except the middle part of the graph, and then this bound works.
Yeah, okay, fine. There is a slight lie here. That is true.
Isn't your delta degree on the same side minus degree across? So there's always some dependence, although it's not going to matter. I'm sure it's fixed. Just saying it wasn't the.
Yeah.
I don't believe
yeah.
it was
Yeah.
Isn't it more complicated? Yeah.
Yeah, you're right. So yeah, the way you should do it is you should restrict to a set of vertices on one side of size epsilon n over 2. Then you should reveal all of the internal degrees on that side and only look at the cross degrees. And that then this argument completely works. But yeah, good question. That would take too much of the slide. Okay. And an argument like this actually tells you that there are very few vertices that have friendliness exactly 0 or 1. And that's why I didn't care about off by 1 errors before, because it just doesn't actually matter. All right. Okay, so the second idea, which I think is one of the main ideas that I'm going to talk about, is iterative exposure of degrees. And this is really the part that I think has a wider application. So hopefully people here might be able to see ways in which to apply this further. And I'd be happy to see that. So let's talk about what so I said we reduced our process to this epsilon n swapping simultaneously. The question is, what do we need to know to analyze this process? So given a specific bisection, we need to know the degree of a vertex into both sides. And we need to know each vertex, its degree to both sides. And once we've done that, we know who's friendly, who's unfriendly, and by how much. And we can find the most unfriendly. And once we do that, we can swap them. And again, maybe we should take like a bit of randomization in which ones we swap, but I'll forego that for now. So instead of revealing like all the neighborhoods and everything like we were thinking about earlier, let's literally reveal this degree information and nothing else. So for example, if at step T, I have a bisection A sub T and B sub T, at this particular step, in order to run the next step, I need to know each vertex's degree to both parts, which I will reveal. And there's maybe some prior information that was already revealed. I can't do anything about that. But other than revealing like 2n more degrees or whatever, I'm going to reveal nothing else. And that is enough to run the next step of the process. Or at least know which sets of vertices are going to be swapped. And then you could say something about it in this new random graph, in this new conditional random graph. So for example, to analyze the first step of the process, I have a random graph G in 1/2, and I have A and I have B, but then I'm going to reveal all of the degrees of each vertex to both sides. So 2 degrees per vertex. And now once I reveal that information, I know who's unfriendly and who's not. Okay, but I'm no longer in G in 1/2. Instead, I'm in a random graph with constrained degrees to both parts. And now I'm going to run this epsilon n swapping process, and I want to say there's a concentration between the number of friendly vertices on both sides, or the number of unfriendly vertices on a single side. Remember, we want to show concentration of the number of unfriendlies at every particular step. And now the point is the remaining information is this constrained random graph model. And hopefully that constrained random graph model has enough randomness in it to still guarantee concentration after performing this one step. Then to analyze the second part, after doing this swapping, not only do I have the original partition, I also have a new partition, and that induces 4 different types of vertices. All the information I've revealed is basically, actually a little less, but basically the degrees of each vertex to each possible part. So 4 parts. In each part, I know the degree of each vertex to each of the 4 parts, basically. And then that allows me to run the next stage. And once I've done that, I have another degree constrained random graph. And so on and so forth, and so on and so forth. And maybe at each stage, you have enough randomness in this degree constrained random graph model to get concentration for the next stage and control the next stage in some reasonable way. And now the punchline is that this isn't really a crazy strategy, because these random graph models are actually well studied and well understood. And they're understood through basically enumerating the number of graphs of given degree sequences. So there's this really rich line of results by McKay and Wormald, where they enumerate dense graphs with prescribed degree sequences. And then there's also a follow-up by Canfield, Greenhill, McKay, which talk about bipartite graphs, which of course we're going to need. So bipartite degree sequences, and how many graphs there are of a given bipartite degree sequence. So then if I want to know in a bipartite graph with a given degree sequence, if I want to know the distribution of the degree of a single vertex, what I can do is I can look at every possible neighborhood, remove that vertex and its neighborhood, and I have a smaller degree constrained random graph. And what I do is I take the number of possibilities using their formulas and divide by the number of total possibilities. And these results are all up to a 1 plus little 1 error. In the dense setting, these things are derived using sort of saddle point analysis of certain contour integrals of generating functions. It's a very beautiful argument, but somewhat technical. And there's actually a rich line of research. Some stuff about sparse graphs was actually known much earlier using the switching method and other techniques. Some of the middle regimes have formed a rich line of research with this work of Liebnow and Wormald, for example. So this is actually a very well understood question in general. As long as the degree sequence of the graph that you're trying to count is not super irregular, this is pretty well understood. There's some technical issues with irregularity, as you can imagine. If you have too many vertices degree n, then it sort of changes things by a lot, for example. But yeah. So we can analyze these degree constrained random models. All right. So what can we do with that? So I'll go through the final idea a little quicker, as it really follows from the culmination of what we talked about so far. So as I mentioned, for each vertex, I can sort of record which of the possible 2 to the k possible histories it can be in, because the partitions at every step induce sort of 2 to the k possible parts that every vertex could be in for the next stage. And at every point in time, if I have a partition into parts piece of I for I and capital I, what I can do is I can sort of record what the degree tuples look like in each part. So in each part, I'm going to record the empirical joint distribution of degrees. So here's a formula to back that up. What I do is I look at all the vertices in a specific part, and I take a random vertex in this part, let's say, or I take the average vertex in this part. Let's look at what possible tuple of degrees it has to every other part, I guess, including its own part. And here I'm just going to subtract off the expected value, or quote unquote expected value, and normalize by root n. And so you should expect these things to look, at the very first stage, actually, you should expect this. So I have 2 parts, and I'm looking at, for every vertex, I'm looking at its degree into its own part and to the opposite part. And this is actually just G(n)1/2. So at the very first stage, mu1 and mu2 should look like two-dimensional Gaussians. At the next stage, though, I take the epsilon n sort of smallest parts of the Gaussians in some sense. I take those vertices and I swap them. And that does something predictable but ugly to the degree distribution. And the dimension also blows up to size 4. So in principle, you could show all these distributions at every stage are close to very certain continuous or almost like well behaved distributions at every step. So I start with a two-dimensional Gaussian for both. Then I use these random graph models to show that I have a concentration of these empirical degree distributions for the next step, the way I described it, by conditioning on what possible neighborhoods each person could have. And then you get some sort of joint degree distribution that is of dimension 4 for each part, and then dimension 8 and so on. But of course, this blows up in complexity and is very, very horrible. So instead, what we do is we just show that this entire empirical distribution at every stage concentrates around some ideal distribution in a very abstract sense using second moment techniques without actually computing what that is. So I'll leave that somewhat to the imagination as we're a little close to the end. But perhaps as a very broad outline, we're going to inductively guarantee the following 4 key properties. So at each step, I have 2 to the k possible parts. I'm going to first guarantee that all of the parts have concentrated size, linear concentrated size. Secondly, for every part, I look at its empirical degree distribution to the that is 2 to the k dimensional to the 2 to the k different parts. And I want it to concentrate around some 2 to the k dimensional distribution. But I don't know what distribution it is. It's just some ideal distribution. Okay, and I'll just abbreviate this notation here. Okay. Furthermore, okay, you're going to need to know something about this ideal distribution. In reality, it should look kind of like a continuous distribution with some Gaussians, and you condition on them and you do some other things and you keep on doing that. In practice, all we need to know is that A, it's an anti-concentrated distribution. So the degree distribution is not too spiky, which is needed to understand how these formulas are evolving in these McKay-Wormwall techniques. And also, we need to know that outlier degrees are pretty unlikely to continue functioning. And so we need to know that this actually has some Gaussian tails in some appropriate sense, whatever that means. And as mentioned, at every step, what I do is I reveal degrees of all vertices to all the parts at a particular step. And since we know that with high probability it satisfies these properties, I assume that those properties are satisfied. Then I run the algorithm. And I show that at the next step, using these degree constrained random models, that the new parts, their vertex sizes concentrate. The new empirical degree distributions concentrate. And the new data is, again, well behaved. And this is the heart of the argument and is quite technical. Takes up a substantial portion of what we do is really getting these guarantees to work out. All right. So that concludes my discussion of how we prove this conjecture on friendly bisections. With the remaining time, I want to talk about a couple further directions. Again, I think that this method is really a more general method. You can maybe see some similarities to the differential equations as we discussed earlier, because there's really a sense in which there's an ideal distribution which is evolving according to some very specified process. But of course, in our case, it's so ugly that you can't write down an ansatz, and you have to do this abstract concentration argument. But really, one of the key elements we're adding here is this enumeration in order to handle these iterated degree revelation processes, where otherwise you would not be injecting enough randomness to be able to understand it. So as just one further application, I want to mention some joint work with Mehtaab Sawhney, who might still be in the audience right now. And we found sort of a further application of this technique to sort of a nice thing called majority dynamics. And I'll just briefly describe the problem and what we can prove, and you can find some of these results. And in our paper. So just briefly, if I have a graph and it's partitioned into two sides, red and blue, the majority dynamics works as follows. Look at a particular step, look at every vertex, and if it has strictly more neighbors on the other side, change its color. You can think of this as maybe like an iterated voting process or something where, you know, I'm connected with people on social media or something, and they have opinions on something. And over time, maybe I update my opinion based on the majority of my friends. Probably not, but you can imagine such a model. And it's studied more generally in these different type of social dynamics areas as well, though, as sort of an abstract version of perhaps, you know, one of these processes. So Tran and Vu initiated and asked some mathematical questions about what this really does in a random graph. And one of their conjectures was that if I have one extra voter on the red side versus the blue side, and I take a random network, then with probability 0.51 or higher, the majority dynamics, if I run it over time, the red side should start to dominate over time. It should be some constant probability, but it should be strictly greater than 1/2. And they were able to prove that the probability is strictly greater than 1/2 as soon as the difference in sizes was at least, I think, 12 or something. And there was further improvements by Berkowitz and Devlin to maybe like, you know, a lead of size 3 or something like 6 or 3 or something like that. But as it turns out, with this sort of new iterated swapping analysis, we can actually precisely compute the probability and say almost anything you really wanted to about this majority dynamics process in a pretty strong sense on random networks, dense random networks. So one example of a theorem that we can prove is that I take I take this G to n plus 1/2, where n plus 1 people are colored red and n are colored blue at the start. And then I do this process where every day each vertex looks at its neighbors, and if it has more of the opposite color, it switches over. Then within 3 steps, this process will converge to either all red or all blue. And we can show that all red occurs with probability exactly this, where this can easily be seen to be greater than 1/2. And this is sort of, this prediction actually basically comes from the probability that red wins the first day in some sense. So in this case, we have to more directly analyze the first step of the process, not just abstractly as in the friendly partitions example, but more directly with formulas. We need to know what the formulas actually give. But after that point, there's sort of a similar abstract concentration arguments and such that are being done to show that once you have a lead, you're not going to lose it. And really, this hinges on knowing that after I reveal the degrees after 1 day, I still have so much randomness that I can still analyze the process at the next step. Whereas the previous arguments really had to use lossy union bounds and other things that always gave suboptimal results, and they could only show the probability is big. They couldn't actually compute it. All right, I don't want to say too much more about that, but here is sort of another application, and I certainly hope to see further applications of this method. So maybe just to sum it all up, here are a couple questions that I have going to the future, further direction. So one is, again, can we find a bisection where every vertex is friendly instead of almost all? Again, there's this bond lineal conjecture that there are finitely many deregular graphs with no friendly cut. There's this conjecture of Bolobosh and Scott where every graph has a bisection where the friendliness is not too large, where again, I think this is easy when, or known at least, when it's not a bisection. And in general, as I've mentioned, more applications of this technique of iterated degree revelation and the study of these sorts of graph processes. All right, that's all I have.
Thank you very much. So we have time for 1 or 2 questions. So please feel free either to ask questions in chat or to unmute yourselves and ask directly. Maybe I could start actually. So does your result actually give that almost all the vertices are kind of epsilon root n away from balanced? I mean, most of them.
So I think
all
the
but
way,
epsilon root n, all but epsilon n vertices are delta root n imbalanced.
I think you can show that like 1 minus f of, so the way this particular thing works, I think what's actually shown is 1 minus f of epsilon root n of the vertices are epsilon n, root n friendly. But there are some heuristic reasons to expect you could actually get sort of, you know, you could decouple this dependence, so to speak, if that makes sense.
So I mean, is it plausible that you could expect in a random graph that every vertex
I would expect that
away from
I would expect that in a random graph there is a bisection where every vertex is like 0.0000001 root n friendly. Yes. Yeah, so that's what I meant. But the way we actually prove this, it only shows that 1 minus f of epsilon n of the vertices are epsilon root n function.
Okay, the other question I had, can you say anything about that? So the process where you just pick random pairs and switch them one at a time.
Yeah.
So do your results say anything about that? I mean, if you batch them up and
yeah.
that in some sense. Or...
So there's some technical difficulties, but I would suspect if you really wanted to analyze this sort of original process, you could potentially do it by, as you mentioned, trying to batch them up. But for convenience, it's much easier to analyze the nibbled process, kind of like, you know, as you've seen, like Rodel nibble, etc. I would be interested if someone could do it in a clean way, but I don't immediately. I think there might be some annoyances. So we just go with the version that, like, this is already actually, the iteration that we go to is already quite technical, as it turns out, from step to step. And so adding an additional complication on top of that wasn't really our intention, but I think it might, I think you should be able to make something like it work, but I'd have to think about it.
Oliver has a question.
Yeah, you sort of mentioned partway along the kind of normal approximation. So that there's a normal approximation where you just sort of take every edge and have its edge weight normal 0, 1. So and then these things are sort of nicer. Does it? I'm not quite sure what my question is. I mean, I guess if that was the random graph model, it would be much easier to analyze because you could do what you do, but you wouldn't need to use these bouquet results and so on. You would just have some normal distribution condition on simple conditions. Is that? Did you sort of think about whether it's possible to connect them back, which I know often it isn't, or sometimes isn't?
So maybe Mehtaab should answer this, but I think once you do that, you get in the regime of a lot of things that are known about certain like statistical physics models. And a lot of things are generally known in these Gaussian cases. So like when you talked about like the max cut, you're really talking about this like a particular like Shannon model or something. And when you go to Gaussians, I think a lot more is known in general about the statistical physics. So there are actually like more general theorems that are just known that can start to nuke some of these like max cut problems and other things. So I don't know off the top of my head, but maybe Mehtaab has a clear picture if he's still here.
Can you repeat the question precisely? So
it was a bit vague about whether the normal model where you take the edge weights to be normal 0, 1. So all the degrees are then a multivariate normal distribution. Is it one of these situations where that's sort of much easier to analyze, but then it's no use because you can't get back to the graph in the end, or would it still be complicated even for the normal model?
So it would be complicated, but I suspect it would be substantially easier because you can rotate Gaussians. Is basically like the nice part of, there's always this Gaussian symmetry. So you can always rotate the Gaussian and calculate everything explicitly. Like it turns out that the formulas in some sense always agree up to constants. So you can, okay, I haven't formally checked this, but I'm pretty sure you can just show like what happens with the Gaussian in this process and what happens with the GN1/2 are exactly the same, because the formulas agree up to constants in some sense. But
like but you have to bridge between like the enumeration and the other thing.
Yeah.
But
the enumeration for Gaussians is like easy in some sense, but for graphs it's very very difficult. Yeah.
And this is really like similar to some of these transference things where like you might expect in a certain physical model, if I replace these Bernoullis with Gaussians, you'd have some similar behavior. But as you mentioned, I think you are right in saying that if I just prove something for Gaussians, I'm not going to be able to extract the result for Bernoullis, unfortunately. Although if someone had a way to do that, that would, I think, would be very interesting.
In a related thing where I tried to do it many years ago, we failed to do that, so it didn't work.
I mean, to give a sense of how difficult this is like, I think the max cut value is known to be n squared over 8 plus some like c n to the 3/2. It's the Parisi formula. But like, if you replace a Gaussian with like a Bernoulli Rademacher, like how far these values are from each other is not well understood. Like this is a pretty hard, like it's little o of n to the 3/2, it's like n to the 5/4, I think, but it's not known what the difference should be. Like stuff like this gets hard very quickly.
Okay. Would anyone else like to ask a question? Zach, did you want to ask a question?
Oh, I don't. I think Alex might actually have a better idea about your particular question. We were just discussing this before the seminar. I think we were saying that, as far as I know, not much is known about the Bulbach-Scott conjecture, but maybe he could say more about your.
Yeah, I don't have anything to add.
Like I think that not much is okay. So I think yeah, I think there should be like of course if you make the one something weak enough, you can always do something. But yeah, I don't know what immediately follows from the literature. I think you'd have to do a bit of searching and see like what immediately follows from what people have proven. But
little o n is known.
Yeah, okay, yeah, sure. For example. Yeah, but I don't know about like quantitatively how much further that goes. That might be an interesting direction.
Okay, so I'd like to thank Ashwin again for a great talk, fascinating result. Maybe we could finish by everyone unmuting and giving a round of applause. Slightly asynchronous round of applause.
And again, thanks for having me. It was a pleasure to speak here.